We're going to talk about section 6.4 in our book, Exponential Growth and Decay. So a separable differential equation is and we'll abbreviate differential equation with DE. So separable differential equations. A differential equation of the form dy dx is equal to f of y times g of x is called separable. And we will only try to solve in AP Calculus separable differential equations. There's other kinds, and we may sometimes see some other kinds of differential equations that are not separable, but we'll never be asked to solve anything other than a separable differential equation. So we do what's called separating the variables by rewriting it in the form f of y dy 1 over f of y dy equals g of x dx. So notice we divided that f of y to the side where the dy was, and we multiplied the differential dx to the g of x side. So essentially what we're doing is getting all the things that have y in them times dy, and all the things that have x in them times dx. Notice that we do this through multiplication and division. So you have to have all of the x stuff multiplying the dx, not being added to the dx. We then, once we separate the variables, we solve it by integrating each side of the equal sign with respect to the isolated variable. Let's see how that looks. So here's our example, dy dx is equal to the quantity xy squared, and we have some initial conditions that y is 1 when x is equal to 1. So first we'll just square that out so we can get x squared y squared. We're going to move the y squared to the dy side, and we're going to move the dx to the x squared side. So this becomes 1 over y squared dy is equal to x squared dx. So now we have separated the variables. All the y stuff is multiplying dy, all the x stuff is multiplying dx. So we're going to then integrate both sides. So recognizing that left side maybe in a more integral-friendly form as y to the negative 2 dy, that's going to become a negative y to the negative 1. And on the other side, when we integrate x squared, we'll get 1/3 x to the third, and we'll put the constant of integration on the side where the x is. Then we're going to, at any point in time, we can solve for the initial condition. So we can do that right now. We'll plug in 1 for y and 1 for x. So this is going to be a negative 1 over 1 is equal to 1/3 times 1 cubed plus c. So that's going to be negative 1 is equal to 1/3 plus c. So we're going to get negative 4/3 for our c. So we now have negative, I'm going to write the y to the negative 1 as 1 over y is equal to 1/3 x cubed minus 4/3. Now we aren't finished until we have solved for the y. So I'm going to multiply through by the negative 1. So that becomes 1 over y equals a negative 1/3 x cubed plus 4/3. Now I'm going to take the reciprocal of both sides. You have to be a little bit careful with how you do this, because you can't take the reciprocal independently there on the right side. That's going to become y, but this is going to become 1 over that whole right side. And I'm going to rewrite it where the positive term comes first, just for aesthetics. You don't really have to do that. So here we are. I don't like fractions and fractions, so I'm going to multiply top and bottom by that least common denominator. And so I'm going to give a new line for this. So we're going to get y is equal to 3 in the numerator, and that's going to become 4 minus x to the third in the denominator. So here is our solution. It's the function that satisfies the differential equation, so it's going to make this differential equation true. It also satisfies the initial condition. Now there's another little subtlety here. A differential equation is only valid on a continuous domain. We can see, hopefully, that because our denominator could be equal to 0, that is 4 minus x cubed is equal to 0 when x is the cube root of 4, that we're going to get a vertical asymptote there, a discontinuity in our function at that point. So we should try to recognize what our domain is for our solution, because it's only valid on a continuous domain. Since our initial condition had x equal to 1, and that means, let me back up a second. So at x equals cube root of 4, we have a vertical asymptote. So we have a continuous domain to the right of cube root of 4, and there's a continuous part of the domain to the left of cube root of 4. Since 1 is to the left of the cube root of 4, then our domain for our solution is only going to be good for x less than the cube root of 4. So I'm going to attach that to our solution. So our solution is y equals 3 over 4 minus x cubed on the domain x less than the cube root of 4. So that's kind of a little deeper level of understanding about these differential equations. That's, at this point in time, probably a little more aspirational. We'll have to get a little bit more practice before that hopefully becomes more second nature. So let's look at another example here. So the law of exponential change, if y changes, this is a common assumption now in population models. So if y, or a population, changes at a rate proportional to the amount present. So what those words mean is it's changing at a rate. A rate means we have a derivative of our population, and that's going to be proportional to, that means some constant k times, and then the amount present is that population, which in this case we're calling y. So that statement, that sentence, if y changes at a rate proportional to the amount present, translates into the differential equation dy dt is equal to k times y. And then if we get some initial conditions, this is what we're going to call the value of y, our population, at the beginning of the time we're interested in. Then the claim is we're going to end up with what you are given oftentimes in pre-calculus or algebra 2 class as a population model. You might be told that, oh, the population is exponential. P of t is whatever the initial population is times e to the kt. And k then is called the growth constant. So it's going to grow, it's going to be exponential growth when the k is positive, and it'll be decaying if the k is negative. Well, let's just see how this works a little bit. So here's our differential equation, dy dt is equal to k times y, and we have our initial conditions. So let's separate our variables and then solve the resulting differential equation. So to move the y to the left side, we're going to divide it. So it's going to become 1 over y dy. We're going to multiply the dt to the other side, to the right side, and k, remember, is a constant that we don't know yet, but presumably if we had more specific initial conditions, we could solve it. So here's our version of the differential equation once we have separated the variables. We will then integrate both sides. So the integral of 1 over y dy is the natural log of the absolute value of y, and the integral of k, a constant, with respect to t, is going to be k times t plus our constant of integration. Now this is a case where I think I would hold off on using the initial condition until we've gotten that y out of the logarithm. Now here's where it gets a little interesting. You have to really think hard about what we're doing and why this works the way it does. To get out of the logarithm, we can imagine that we are going to either write the corresponding exponential, or sometimes we can say we're going to exponentiate both sides. Now, e to the natural log of the absolute value of y, it would theoretically still be an absolute value of y, but I'm going to talk about that in a moment here. On the other side, we have this e to the kt plus c. Now, this comes up so much, we are going to, I'm going to show you why it works the way it does here, but we won't necessarily have to demonstrate all of these steps along the way. Using our property of exponents, we know that x to the m times x to the n, when you multiply two powers with the same base, you add their exponents. we're going to go right to left here. Since we have this addition in the exponent, that means that could be written as e to the kt times e to the c. Now, e to the c, remember c is a constant that we've not yet determined, so e to the c is still some unknown constant. So what we can do then is rewrite this e to the c as maybe just a little bigger c, e to the kt. That is, we're going to go from this right here to, we'll skip this step in general and jump right to here. And in fact, we're even going to drop that absolute value of y. And let's think about why that might be. So what this is saying is that if you have an absolute value of y equals something, then y could either be the positive or the negative of that. So this absolute value of y is saying that we could get y equal to a positive exponential, or we could get y is equal to a negative exponential. It couldn't be both, because then it wouldn't be a function. So what we're going to do, we can actually drop the absolute value without any penalty, because we have not yet decided what that constant is. That's going to come from our initial condition. So we can safely say and correctly say that y without the absolute value is c e to the kt. Now, that c could be a positive or a negative, and that will be determined by the initial condition. So what we will do, the shortcut of the whole thing, is we will go from where we have solved this differential equation. We've integrated both sides in the process of solving that differential equation, and we're going to shortcut it and go straight to here without writing all of this stuff that we did here to get the c to be the leading coefficient, and without having to worry about those absolute values. Okay, now we can use the one initial condition we have. When t is 0, y is going to be y sub 0. So plugging y sub 0 for the y, we're going to get c e to the 0, and that tells us that our c is the y sub 0. Now, presumably, y sub 0 could be positive or negative, and that's going to count for the possible absolute value of y. So at the end of the day, our solution is going to look like this. And we can see that whether this is exponential growth or decay is going to depend on that value of k, which we could solve for if we had a second initial condition. Okay, well, that was a long-winded explanation for that one. Let's talk about the next example. If a sub $0 are invested at continuous interest, then the rate of change is proportional to the amount in the account. So if we say a of t is the amount in the account at time t, then the rate of change is dA dt is proportional to, means k times, the amount in the account is that a. So we get the same differential equation that we saw a moment ago talking about population models. And again, just so we can practice it, we'll separate the variables. We'll get 1 over a dA is equal to k dt. And we will we'll integrate both sides, We'll get the natural log of the absolute value of a is going to be kt plus c. We're going to go straight to a equals c e to the kt. So we don't have to show any other work, those steps in between there. And then do we have a sub 0 is the amount we have at time 0. So the a sub 0 is what we have at time 0. So plugging in 0 for the t and a sub 0 for the a tells us that the initial amount c is a sub 0. And so we get something that looks like this, and you might recognize this as our PERT formula from way back in your Algebra 2 days, and we did that in AP Prep 2, where that's the initial amount, that's sometimes called the principal, and that's going to be the continuous interest rate. That's going to be that growth rate. Okay, so let's find the half-life of a substance with decay equation equal to y equals y sub 0 e to the negative kt, and show that the half-life depends only on k. So if our half-life is whatever it is, then we're going to say that we'll have, that we know that we have y sub 0 at time 0. That's going to be our population at time 0, because you put in 0 for the t, then you get e to the 0 times y sub 0. So half of that will be 1/2 y sub 0, and that's going to be y sub 0 e to the negative kt. So we're solving for the t, because that's going to be our half-life. That's how much time will it take for us to have half as much as we started with. So you can see that the amount we had to start with doesn't matter, because that's going to divide out. We're just going to have 1/2 equals e to the negative kt, and we're going to try to solve that for t, so we can take the natural log of both sides. And now we get a chance to flaunt our logarithm skills and know that the natural log of 1/2 is the natural log of 1 minus the natural log of 2, and the natural log of an exponential base Euler's number, those are inverses, they cancel each other, and we're just going to get a negative kt. We also know that the natural log of 1 is 0, so we have negative natural log 2 divided by negative k is our half-life. And so if we cancel those negatives, we're showing that our half-life, how long will it take us to have half as much, depends only on the k. Okay? Let's see. Population of hornets grows from 10 on May 1st to 50 in 30 days. When will the population reach 100? So we're assuming here that because this is a population, that its rate of growth, its growth rate, will be proportional to the amount of hornets present. And we get our usual differential equation. dp dt is equal to k times p. We'll hopefully do what's kind of getting routine, separate the variables, integrate both sides, get the natural log of the absolute value of p will be kt plus c, which means that p is going to be c e to the kt. Since we know that we have 10 at time 0, that our population of hornets is 10 at time 0, that's going to tell us that c is equal to 10. So we know that then p is going to be 10 e to the kt, and we want to know, it goes from 10 on May 1st, so it's going to be, we're going to get a population of 50 when t is equal to 30. That's going to allow us to solve for that k. So we're going to say 50 is equal to 10 e to the 30k. We'll divide by the 10 and get 5 is e to the 30k. We'll take the natural log of both sides, and we know that taking the natural log of an exponential base Euler's number is just f of f inverse. Those will cancel, and so we are going to get our k to be, our growth rate is natural log 5 over 30. We can take that to our calculator in a moment here. We want to know when will the population be 100. So we'll put 100 in for our population. We know the initial value was 10. We have e to the k, which we decided was natural log 5 over 30 times t. And we're going to solve for the t to find out when. So we'll divide by the 10. So 100 divided by 10 is 10. We have e to the natural log 5 over 30 times t. We'll take the natural log of both sides and know that that will get us to, I'm going to come up here, natural log 10 is equal to our natural log 5 over 30 times t. So t is going to be 30 natural log 10 divided by the natural log of 5. And when I did that, what did I get? About 42.920 days. 42.920 days. Should have left myself a little more room there. Okay, let's try another example. Whoops. So All right, let's do carbon-14 has a half-life of 5,700 years. Find the age of a sample in which 10% of the radioactive nuclei present have decayed. So if 10%, and we can, I think, get to just our P equals, should we say P sub 0 e to the kt is going to be our equation there. And if 10% has decayed, that means we still have 90% of what we started with. And we want to get the age of that, so we're trying to solve for the t. We can divide out the p sub 0. It doesn't really matter how much we had to start with. So we have 0.9 is equal to e to the kt. We can take the natural log of both sides and know that the natural log of e to the kt is going to be just kt. Oops, I did this in the wrong order. Let me save that for a moment. We better go find out what the k is. So I haven't used the half-life part yet. So let me back up here and say half of what we had to start with is going to be e to the k times 5,700. So we need to solve this for the k, and then I'm going to come back to that other equation. So again, dividing out the p sub 0 is 1/2 e to the 5,700k. We'll take the natural log of both sides, and can never pass up an opportunity to use those properties of logarithms. Don't want to forget those. And so we'll get that our k is negative natural log 2 over 5,700. So then we can come back now to our equation that we left hanging here, and we can say that our k is this negative natural log 2 over 5,700 times t is equal to the natural log of 0.9. So we can divide that over. So we're going to get the natural log of 0.9, and we're going to do the 5,700 over negative natural log 2. However you want to enter that into your calculator. And when I did that, I think I got 866.418 years. So that's how old that sample is. All right, Newton's law of cooling. Let's take a look at that. So Newton's law of cooling says that the temperature, capital T, of an object, and we're going to measure that in degrees centigrade, and time is going to be little t. So capital T is temperature, little t is time. Capital T sub s is the temperature of the surrounding medium. Is it the air that it's in? Is it in water, or whatever it might be? So our differential equation is d capital T dt. So the change in temperature with respect to time is negative k, some constant, times the difference between the temperature, capital T, and T sub s, and that is our temperature of the surrounding medium. I said that, I guess, already right here. So that's the difference between the temperature of our object and the temperature of the surrounding medium that object is in. Okay, let's just separate our variables here. So remember, this T sub s is some constant. The capital T is it's like our y, that's our dependent variable, and the little t is the independent variable. So we want to move this capital T over to the side where the d capital T is, but there's no way to do that without dragging this constant T sub s with it. And that's not a problem, but don't get hung up in trying to separate those off. That's not going to work. So we're going to get 1 over capital T minus T sub s d capital T is equal to negative k d little t. So now we've separated the variables, so we can integrate both sides, and we're going to get on the left side the natural log of the absolute value of t minus T sub s. And on the other side, that k is a constant, we're integrating with respect to little t, and we're going to put the constant of integration on the right side. So we're going to do our exponentiate both sides idea, and that's going to become capital T minus capital T sub s is going to be CE to the negative KT. And I think that's all I want to do with that. So, I guess if we want, we could say that the temperature at time 0 is going to be T sub 0. So then if we put in T sub 0 for that initial temperature minus that T sub s, the temperature of the surrounding medium, and put 0 in for the little t, that will tell us what the initial, what the constant, that coefficient of that E is. It's going to be that crazy thing, which would then be, we can say T minus T sub s is going to be that constant T sub 0 minus T sub s times e to the negative KT power. So you might see something like that as a formula given in some kind of physics textbook or something like that for Newton's law of cooling. We're not going to try to memorize that or anything like that. Just kind of an interesting thing to try to actually work out. So let's see how we can use this idea. We're not going to just use the formula. We're going to use the idea to create a new differential equation and solve it. So we can still use the differential equation we created up here. That's the part we're going to steal. So the change in temperature with respect to time is negative K, where K is some constant that we're going to try to solve for, times T minus the T sub s, the temperature of the object, minus the temperature in the surrounding medium. So let's see, a hard-boiled egg is 98 degrees centigrade, so that's going to be our temperature at time 0 is 98. So there's one initial condition. It's put under running 18 degrees centigrade water. That's our T sub s. That's the temperature of the surrounding medium. And we want to know what, we do know that after 5 minutes, the temperature of that egg has cooled to 38 degrees, and we want to know at what time will that temperature reach 20. Okay, so let's see what we know here. I guess we know the T sub s is 18, so we can say d dt, d capital T, d little t is negative K times, this is our temperature function, minus the 18 is the temperature of the surrounding medium. We'll separate our variables by dividing the T minus 18 to the left side, leaving the d capital T there. We'll multiply the differential d little t over to the right side. We'll integrate both sides. So on the left side, we're going to get the natural log of the absolute value of t minus 18. And on the right side, we're going to get a negative kt plus the constant of integration c. We can exponentiate both sides to get out of that logarithm and get t minus 18 is equal to c e to the negative kt. So hopefully this is getting a little bit more kind of routine. Now we have two things we don't know, the c and the k, and so we need two initial conditions, which we have. Here's our first initial condition. So if we plug in 0 for t and 98 for the capital T, we're going to get 98 minus 18 is c e to the 0. So that's going to tell us that c is the 80. So we've now upgraded our equation. So now we have t minus 18 is 80 times e to the negative kt. So now we're going to use our second initial condition and try to find out what that k is. So we're going to plug in 38 minus the 18 is 80 e to the, and that's going to be a negative 5k. So 38 minus 18, I think, is 20. We'll divide the 80 to the other side in preparation for solving for k. So that's going to be 1/4 is e to the negative 5k. We'll take the natural log of both sides, once again giving us an opportunity to flex those logarithm muscles. Natural log 1 minus natural log 4 is negative 5k. Natural log 1 is 0, so we have negative natural log 4 over negative 5 is our k. And we can either punch that into our calculator and get a decimal, or just leave it like that, either way. So that is, I'm going to slide the screen up a little bit here, so I have a little bit more room to work with. So we want to know, when is the temperature going to be 20? That was our ultimate goal. Let's maybe write down our equation, where we are right now. So we had the t minus 18 was equal to 80 e to the negative kt. And so we could even say t is 18 plus 80 e to the, and the k we said was natural log 4 over 5. So that's going to be a negative natural log 4 over 5, or whatever decimal you want to put in for that. And then we want to know, when is the temperature going to be 20? So we can then plug in for the capital T, the 20, because that's going to be our temperature. And we have 18 plus 80 e to the negative natural log 4 divided by 5t. So subtracting the 18, dividing by the 80 gets us to this place right here. So that's going to be, I guess, 1/40 is equal to e to the negative natural log 4 over 5t. We can take the natural log of both sides, and we've done this a few times now already. So that's going to be natural log 1 minus natural log 40 equals negative natural log 4 over 5t. So that's going to be a negative natural log 40, and we can, I guess, multiply that by 5 over negative natural log 4, and the negatives will cancel, so we'll have 5 natural log 40 over natural log 4, and I believe when I did that I got something like about 13.3 minutes. All right, very good.